Sir, what you? No, that was going right. All right. What questions do you have? No questions? Things are all right? All right. Well, let's continue on with our discussion of, pardon me, general inner product spaces. So remember again, we can define, well, if they satisfy the axioms, you can define inner products more generally than what we talked about for the standard dot product on our end. And remember again that our axioms are these four, mentioned these last time, that whatever you're going to define as your inner product has to commute, needs to distribute over vector sums. You should be able to move your scalar to either a piece of the inner product or pull it completely out. And if you do an inner product with itself, you need to get something that's not negative. And the only way to get an inner product that's zero is if the vector was zero to start with. So those are the four properties of being an inner product. We talked about a more general one for polynomial spaces last time. But basically we said, looking at that particular one, it pretty much looked like a standard Euclidean dot product. If we think of the coefficients on the x squared, the x, and the constant, just as components of a vector, looked similar. One that gets a little bit more interesting, which we didn't get a lot of chance to write down details of, but we will come back to this one later on when we start talking about some least square stuff here, hopefully later this week, but definitely by next week, where you've got continuous functions on some interval. Again, it doesn't make sense to think about components of functions, right? Right, we think of functions as vectors more generally, but they don't have components. So if we're going to define an inner product, it needs to be done in a different way. And that way, in this case that we've got written here on this paper, is that we can do the integral of the product of two functions. That's why we want continuous functions, to make sure that we can always integrate. And we know that the product of two continuous functions is continuous. We can see why our four axioms are satisfied pretty quickly. So that's just properties of integrals, right? If you do your, oops. Do this real quick so I don't keep moving things. Set this background last time. Sorry about that. No. Just take it. Stop. Two, two. Set this background. Did it move something on me? Sorry. Let's try to get back to where I was. Yeah. It looks like I missed a page on there. Now that I have it, let me make sure. No. All right. Well, anyway, sorry. Let's look at why this is true a little bit, why it satisfies those axioms. So again, if I have the inner product of P and Q, if I want to make sure that that's the same thing as the inner product of Q then P, well, the definition says that I'm doing the product of those two functions, right? But this is just inside here, this is just multiplication of two functions. These functions are real valued, meaning if you plug in a number, you get out a real number. Plug in a real number, you get out a real number. Real number multiplication is commutative, so that will flip around as Q of X, P of X, and that gives us that commutative property that we want. That's one property, right? What does the inner product of P of X with a sum of, say, a Q of X and an R of X look like by the definition that we're using? Well, we need to prove that, right? That's what we're trying to prove. Okay. What does it look like as far as the definition for our inner product in this case? Yep. So P of X times. Yep. Good. That's how the inner product is defined here, right? Thank you. Yep. What do we do next? Yeah, I think we had to distribute it. Yeah, don't we? Yeah. So I need to distribute that P of X through. And then what can we do, since we're doing an integral, what can we do with respect to the sum? Break it up, good. First one, by the definition that we came up with, what do we recognize the first one as? Yeah, that's the inner product of P of X and Q of X, and the other one is. So that shows that it satisfies that second property. The third property would be similar. What did we use here, really? We just used the plus to break up our integral, right? Because we know that integrals break up over sums. If I had a constant in there, we know that the constants would pull out in front of the integral. That's why the third one will be true. The fourth one, if you do the inner product of P of X with itself, you ended up with the square of the function, right? Can that ever be, if I do the integral of the square, can I ever get a negative number? No, because the function's always non-negative. It's continuous. So when I square it, it's certain, and the continuous part's going to be for the second part. When I square it, it's non-negative. So I can't get a non-negative for an integral. So it has to be greater than or equal to 0 by our properties of integrals again. And the only way it can be 0, if I had the integral equals, oops, for my dx, equaling 0, the only way that can happen is if the inside here is 0 because it's continuous, right? If it weren't a continuous function, I could have an integral be 0 and the function itself not be identically 0 all the time, because I could redefine the function at a single point. Remember that the integral of a single point is always 0, so you could do weird things if you had a non-continuous function. But this is, since it's continuous, I know that that happens only if the function is equal to 0 itself. So we really do get an inner product. And again, that fourth property really allows us to be able to define lengths. So using this particular inner product, I can talk about lengths of functions with respect to this particular inner product. That's what that fourth property does. Yes? Is that it? The third property is just like this one. You would just take your constant and move it out in front. You'd have the C times the P of X here, and then I can pull the constant out in front, or move it with the Q. You should be able to do that one. It's just using properties of integrals again. So for general inner products, we should be able to prove certain. I don't know why I've got that one. That is the definition. Anyway, I think it's because when I came up with these, the definition had it in the front as opposed to in the back, but we'll talk about it here in a second. In that first one, it says if I inner product the 0 vector with any vector, I get the number 0. get the scalar 0. How do you think we should start that? We've done this technique before. How do you think we should start it? Like quietly. We've done this technique before this section.
So like make 0 looks different.
Make the 0 look different? How might we like make it look different? Yeah, 0 plus 0, right? We've done that technique before because what does that allow us to do now? Well, that's for vector space stuff, right? As far as the inner product goes, maybe if I write it as an actual dot versus with the notation with the brackets, what does that allow you to do now? Distribute, right? Now, technically, the distributive axiom actually looks like this one. I've written this one backward of what I wanted. The distributive axiom looks like that one, doesn't it? On the right component. Why does distributivity also work over the left component? Which axiom allows you to go ahead and just distribute over the left as opposed to the right by just rewriting to start with? I can just flip them, right? I can do commutativity, can't I? If I write it this, whoops. If I write it this way, that's the same thing, isn't it? Okay. So that's what's going to allow us to distribute. So I might as well just distribute it here. I get 0v plus 0v. Oops. And now if I think about this part right here being equal to that part right there, what can I do to both sides? Is to subtract the 0 comma v, right? It's some number. Inner product gives you a number. So if I subtract from both sides, we'll get 0 equals 0v. And again, this is the number 0 here. This is the vector 0 here. When you do an inner product of two vectors, do a top product of two vectors, you get a scalar. You get a number. Yes.
And then second one.
So that should be a vector.
No.
Oh, above it, yep, that should also be one. Yep. All those on the inside should be vectors. Thank you. This one I meant to write the other way around. I meant to write this as, let me cross it out. I meant to write it out as v plus w comma u. Again, that's not a huge surprise because the axiom is written the other way around, isn't it? It has the sum in the right component. Well, how would I use that distributive property? You would just commute these two things around, distribute, and then commute back. That would be how the proof would go. Start with this. Use the second axiom to flip them around. Sorry, use the first axiom to flip them around. Use the second axiom to distribute, and then use the first axiom again to flip them back around. And then, likewise, this is just writing something as an additive inverse. So these properties shouldn't be that big of a deal to prove using the axioms. In any event, they behave like you would expect them to. That's the big problem. That's the crux of the whole thing. All right. So again, we said that we define inner products to hopefully get us to an idea of angle measure. We've already seen that our angle measure formula for Euclidean vectors, I want to write it off to the side. We're going to get to this eventually. But remember that for Euclidean vectors, it was the dot product over the magnitudes, right? Okay. Now, in order to do this for any two vectors, what needs to be true about this expression right here in order to be able to do the inverse cosine? What has to be true about what I just circled in order to be able to make sure that it's always going to be defined when I do the inverse cosine? Or said it another way, what do you know the cosine is always in between? Let's start there. 1 and negative 1, right? So in order to be able to do the inverse cosine, that better be between 1 and negative 1, right? So it's not worrying about the negative sign. What better be true about the top relative to the bottom in size? The top better be smaller, right? Or at least no bigger, correct? So when we get to general inner products, we better have that same property. Okay, we better have that same property when we get there, otherwise we're going to have trouble being able to define angle measure. Okay, and we'll see that here in a minute. But notice that part of our formula, besides being inner product, is also length. Okay, so we should be able to define the length or the magnitude or the norm. And we talked about how we could define that generally back when we did it for Euclidean vectors, but just to write it down again. We define the length or magnitude or norm of any vector as the square root of the inner product. Oops, I used dot. Sorry, I got a little excited. I should use those brackets. I should have brackets around it. I fixed it. It should be the square root of the inner product of the vector with itself. Okay. We know that this is okay to define it this way because what has to be true about the inner product of a vector with itself? What always has to be true about that? Can that ever be 0? Or I'm sorry, can that ever be negative? No, so we can always do the square root of it, right? So we don't have any issues there. Okay. We also define distance between two vectors. Remember how we defined that before? Oops. How did we define it for Euclidean vectors? Soon we forget. Yeah, you do the v minus u or the u minus v and you do the length of it, right? Order doesn't matter. You do u minus v or v minus u and do the length, right? Now that we have a notion of length or magnitude for any inner product space, we can do distance between vectors for any inner product space. Notice, and this is important for function approximations, notice if we had that, going back to that example, with the continuous functions on the interval from a to b, that inner product. We can also talk about distance of p of x between p of x and q of x using this definition. This will be the integral from a to b of p minus q squared, and then take the square root, right? Because the definition is subtract the two vectors and then take their length, right? That's the definition of distance. Okay, so I subtracted the two vectors and then took its length. Well, the length is the square root of the inner product with itself. Okay. Notice in some sense, this, when you do p of x minus q of x, if you think about just, a couple of arbitrary functions, doesn't matter. Say this is my f of x and this is my g of x. When I do f minus g, and do the integral, that gives me that area, doesn't it? When I'm squaring it, I'm making all of that stuff positive. So basically, we're saying that the distance in this sense, in this particular vector space, the distance between the two functions really talks about how much gap is there between them. It's in terms of the gap between them, right? The squaring part makes sure that we make all of this positive. It'll like stretch it out some. But really, we're talking about how close together are they. The smaller that value, the closer together they are. And again, the whole reason why I said we're talking about this particular one is to do function approximations. If I want to approximate one function with another, do I want that gap to be big or small? Small, right? So I want to somehow get a handle on making this small, right? I want to make the square, in some sense, the least, or a least squares idea. If you've done any statistics at all, there's least squares idea. This is a least squares idea later on that we'll talk about. Like I said, either later this week or early next week. But this is why we care, by the way. Okay? Well, that's why some people care. You personally may not care, but that's why people care about this. Okay? It's important for doing approximations. All right? Okay. So let's see if we can just put some of this stuff to use. Let's talk about a quote-unquote weird inner product on the polynomial space. This is different than the one we talked about before. And see if we can use it to do the inner products on these things. So we have two second degree or less polynomials, and we'll define the inner product as plug in 0 to both of them, multiply it together, plug in 1 to both of them, multiply it together, plug in 2, multiply it together, and then add. Okay? You can show that this is an inner product. I'm not asking you to do that here. We're just going to play with it and see what answers we get. So in this particular case, I want to do P of 0, Q of 0, right? So I'll plug in 0 into the first one, plug 0 into the second one. What do you get when you plug 0 into the first one? 2. What do you get when you plug 0 into the second one? 3. Good. Okay, so that's the first product. That's this piece. What do you get when you plug in 1 into the first one?
Oh, I'm sure. 1, 2, 3, 2.
2. You get 1 minus 1 in that second part, don't you? You get a 0 again, don't you? And then what do you get in the second one? 4. Good. Okay, 2 times 4. Good. The last one, when you put in 2, 0, and doesn't matter what I get, but I get 7, don't I? So 8 plus 6 gives me 14. That's the inner product. Okay? It's defined weirdly, but that is the inner product, right? Just do that computation. That's all it's asking you to do. Okay? I mean, it's a weird formula, right? But it's not a hard computation. Put in 0 into both, put in 1 into both, put in 2 into both, multiply, add. Right? Okay. For length, norm, magnitude, those all mean the same thing. For magnitude, I want to do the square root of the inner product with itself. Right? Well, we've already computed the values for 0, 1, and 2 for that particular function, didn't we? Okay. When we put in 0, we got 2, so we'll do 2 times 2. When we put in 1, we also got 2. And when we put in 2, we got 0. So we should have 2 times 2 plus 2 times 2 plus 0 times 0. Those numbers should be the same, right? Because it's the same function we're plugging it into. You're going to be simplify, you get 2 root 2. Yes. Got it? Okay. again, I know that inner product is weird, right? It's different than what we're used to. But once we have the formula, we're just plugging in the numbers into the formula, right? What do we do next for the distance? By definition, what is the distance? What do you do?
Standard for the vector unit.
Good, vector u minus vector v, right? Don't know why sometimes. Hardest time with the technology. All right? Here's my vector u, here's my vector v. What do you want to do with those two things? Well, gotta do something first because you just told me what the formula was. It was vector u minus vector v, right?
Yeah.
What do you want to do first? Okay, let's then do what with the two functions? Subtract them, good. So what do you get when you subtract the two functions?
Was it 3x? What's it?
2x squared, right? So you get negative x squared minus x squared. Did the order matter? Could you have subtracted the other way too? Yeah. Okay. So again, the first thing you do, if this is your u and this is your v, the first thing you're going to do is u minus v, right? We agree? Okay. Okay, what do we do next? 0, 1, and 2, and multiply by itself, right? Because remember, this is the square root of the inner product with itself, right? What do we get when we put in 0? Negative 1. What do we get when we put in 1? Negative 2. And what do we get when we put in 2? Negative 7. That's what I got when I put it in. Now again, why am I writing it twice? Why am I doing negative 1 and negative 1, a negative 2 and a negative 2, and a negative 7 and a negative 7? Because it's multiplied by itself, right? It's P of, remember that's P of 0, Q of 0, but the P and the Q are the same here now, right? Okay. 1 plus 4 plus 49, 54. Is that right? 54 is 9 times 6, so you get 3 root 6 when you're done. I don't really care if you simplify the last part. Is that all right? Just playing around with a different definition? Okay. All right. This next one just wants us to play around with the properties. They tell you some inner products and some lengths, some magnitudes, and then asks you to compute. Doesn't tell you what the vectors are, does it? No. Okay. All right. So what do you think we should do first? What if you had something, again, instead of writing it with the brackets, what if I had something with the dots like this? What might you do first? You distribute it, right? Basically, it looks like a kind of a FOIL idea, doesn't it? Still works with inner products as well. So we can write this as the inner product of u and v plus the inner product of u and w plus the inner product with v and v plus the inner product of v and w. What did I do basically? I did a kind of a first, an outer, an inner, and a last, right? Didn't I? Just distributed it. I know it looks weird with the brackets, but that's all we did, right? Okay. Do you know what the inner product of u and v is? 2. Do you know what the inner product of u and w is? 5. Let's skip the next one. Do you know the inner product of v and w? -3. Okay? Those were given to you, right? You're also given the next one. What is the inner product of V with itself? Why is it 4? You're exactly right.
The magnitude.
Good. Right there. It says the magnitude of V is 2. Remember, the magnitude is defined as the square root of the inner product with itself. So if you square both sides, inner product with itself is magnitude squared. Right? 711 minus 3 is 8. Should be able to do the same thing with the next two, right? Let's do one of them together and you can do the next one for practice. What do you get when you basically, quote unquote, FOIL out that part? Okay, and a 2V and a 3U. Okay, a 2V and a 2W. Next one would be
Negative U.
basically the same thing we did in the previous one, isn't it? Okay. What can you do with all the scalars? Bring them out, all right? I can bring out the 2 and the 3, so that puts a 6 out in front of this one. I can bring out a 2 and a 2, it gives me a 4 out in front of that one. I can bring out the -1 and a 3 to give me a -3 out in front of that one. And a -2 out in front of the last one. You might have just saw that you could have gone from the first line to the third one, right? You could have just pulled them out at the same time, if you're comfortable with it. Do we know the answers to all of those now? Inner product of V with U is 2, because remember it's commutative, right? We know that the inner product of U and V is 2. We can flip it around and get 2 for the other one. V and W, -3. U and U, was just 1, because 1 squared is 1, right? And then the last one, U and W, was 5, right? Whatever that simplifies to. What the calculator's for. Not that I couldn't do it, but I just don't feel like. That okay? Notice you can do the next one as well. I'll leave the next one for practice. Let's look at the one of these with a sum in it. Again, this is the square root of the inner product of the vector with itself. What might you do next, do you think?
Uh,
Do you think we should do next? Distribute it again like we did in the previous one, right? This will be U inner product with itself. You'll get a U inner product with V. You'll get the reverse. And you'll get V inner product with itself. And do we know the values of all of those? The value of the first one is 1. The value of the next one is 2. And so is the next one. Value of the last one is 4, isn't it? Because it's V, right? So what do we get? 3 when we're done? That okay? Does it make sense what we're doing? Just using those properties? Okay. All right, I'll leave those last other ones there for practice. Let's talk about how we can use some of these to prove an identity. Probably familiar with identities from trig class. This is a similar way to do a similar kind of idea. When we say it's an identity, we mean it's true for anything that we can plug into both sides of the equation. Says the inner product of u and v is the same thing as a quarter of the inner product of u plus v squared, and then a quarter of u minus v squared. Your typical way for verifying an identity is work with one side and make it look like the other. And kind of a rule of thumb is work with the more complicated side first. Which side's more complicated, the left side or the right? The right is, isn't it? Okay. So let's start with the right-hand side. The whole reason why I'm doing this particular one is just to try to reinforce the idea of how to rewrite these magnitudes. Another way to rewrite magnitude squared is what? The inner product with itself, right? Minus. And again, another way to rewrite the inner product with itself, or excuse me, the magnitude squared is the inner product with itself. Because now what do you think we can do now that we have these written as inner products? Distribute, right? So we'll have a u with itself. We'll have a uv and a vu. But remember, the inner product commutes, doesn't it? So I can rewrite that as a 2 inner product of u and v, and then an inner product of v with itself. Forgot my pointy bracket first. What's the only difference going to be when you do the distributive property on the right-hand side? It'd be a negative 2 u inner product of u and v, right? There's a minus instead of a plus. What happens now? Anything go away? That one kills that one off, doesn't it? Even if you distribute the minus one or the 1/4 through, but they have opposite signs, don't they? Those go away. Those go away. When I distribute the minus 1/4 through here, you're going to get a plus 1/2, aren't you? So we really do end up with UV when we're done. Yes.
Why
don't these go away? When I take that and distribute it there, I get a plus sign. Right? That one okay? That one wasn't too bad. So anyway, that's playing around with length. I told you that the whole reason, well, not the whole reason, but a good amount of why we care about inner products is to define things in terms of angle. We said before that in order to make that cosine formula work, we better make sure that the top is no bigger than the bottom in absolute value, right? And that's exactly what the Cauchy-Schwarz inequality says, that for any inner product space, the absolute value of the inner product of u and v is always less than or equal to the product of the magnitudes. That's the Cauchy-Schwarz inequality. So again, notice that that's exactly what we said we needed in order to be able to do the inverse cosine of that fraction, right? Okay. And again, the whole reason why we want angle measure is really the idea of perpendicularity, or more generally orthogonality, and we'll talk about why that's important in the next section. Okay. I do want to prove this real quick, because of course I do. I'm a mathematician, I want to prove it, right? All right. So to start with the proof here, we're going to start with a function, not x. I'm going to start with a function of t, and it's going to be the magnitude of tu plus v squared. Well, what's another way to write magnitude squared again? Yeah, the inner product with itself, right? Oops. Inner product with itself. What do you think I might want to do with that inner product with itself now, given the last couple of problems we've done? Distribute everything, right? When we distribute, I'm going to get a t squared, right? And then I'll get a u with itself, right? How many of the next ones do we get? Well, I'll get a tu with a v and a v with a tu. So we'll get a 2t uv. And then the last one will just get a v with itself. Okay? Now, two things I want to ask you. What kind of things are these inner products? What kind of objects are they? When you do an inner product of two vectors, what do you get out? Scalar, they're numbers, right? They're just numbers. So as a function of t, what kind of function is f? You get a number times t squared, a number times t, and a constant. What kind of a function is f? So yeah, with specifically what kind of polynomial? Quadratic, right? It's a quadratic polynomial, we agree? Okay, cool. We know lots of things about quadratic polynomials. That's number one. Number two, what can this expression never be? It can be zero, but what can it never be? Negative, right? It can never be a negative value, right? Okay? So you have a quadratic that's never negative. So either it doesn't cross the x-axis or it just touches it, right? Okay? We agree? Okay. So I'm going to write that down. So note that f of t is a quadratic that is never negative. Okay? So if you were to apply the quadratic formula, or your quadratic formula, if you were to apply your quadratic formula, pardon me, what's going to have to be true under the square root if you don't get any places where it's going to cross the x-axis, or it just goes down and touches and goes back up again? What has to be true about under your square root? Or your quadratic formula. If this number right here is bigger than zero, how many roots do you get? Two. I add something and I subtract something, correct? So what's the only way that you're not going to add or subtract something there? What has to be true under the square root? It's either zero and it just touches, or it's negative and you don't get any real roots, right? Okay. So that's what we have over here, isn't it? So remember what we call this under the square root? The discriminant, right? So what is the discriminant here? What is the coefficient? What is b? B is the coefficient on the x term or the t term, right? What is b? 2 times the inner product of u and v, right? So we have to have 2 times the inner product of u and v squared minus, what's a? Yeah, the inner product of u with itself, and what's c? Yeah, it's the v and v, right? Here's your a, there's your b, this is your c, right? And what does it have, what has to be true about this expression? So yeah, less than or equal to 0, right? Let's rearrange. I square both of these things, I'll get a 4 inner product squared. Is less than or equal to 4 times. What's a better name for this? That it just underlined? Magnitude of u. Better name for this? Magnitude of v. Divide both sides by 4. Take the square root. When I do the square root of a square, I get absolute value. So I get the result that we want. Oh, this should be magnitude squared on those, by the way. Because we don't have the square roots on those, so we get magnitude squareds. So this gives you your Cauchy-Schwarz inequality. Again, not that it's necessarily the end-all, be-all type of proof ideas. It wasn't a bad proof, though, right? Just had to remember a little bit with quadratics. It's the Cauchy-Schwarz inequality which makes angle measure possible in any inner product space. Okay? And again, this is important later on. I know I keep pushing things off, but it's important later on because we need the concept of orthogonality to help us with the idea of finding least squares approximations. It's what helps us later. Okay, that's why this is important. All right, you should be able to do these proofs pretty quickly. It's a matter of just rephrasing these things in terms of the definitions with the inner product. Okay. The only one that's a little bit trickier is this one, but it involves the Cauchy-Schwarz inequality. But for example, if you look at number 3, how can I rewrite this right here, the thing that I underlined in number 3? Well, that's the idea. That's what we're trying to prove. How do we rewrite this as definition? Yeah, good. It's the square root of Ku and Ku, right? When you take the K out, I got to take it out of both terms now, right? So I get a K squared. And then when you do the square root of a square, you get absolute value, right? And what's a better name now for what I have under the square root? Magnitude. Good. That's the proof of that one. So these are all just proofs of rephrasing things. I will tell you, if you want to practice on number 4, I would do the square of this and play with that. Okay? Start with start with u plus v squared. You'll need to use the Cauchy-Schwarz inequality to prove it. I will tell you that. Okay. But start with that and play around with it. Okay. Yes. Same thing what I started with, the absolute value of what I started with. Anytime you do the square root of the square, it's always absolute value because of this. Here, what did I plug in first? -2. What did I end up with? +2. I didn't end up where I started, right? If it's a negative, I have to do the absolute value because the squaring gets rid of the negative.
So this is
What's it?
it's
It's positive. I don't have to worry about the absolute value, but it doesn't tell me what K is. It just says K is a scalar. K could be negative. There's nothing about that that tells me that K couldn't be negative. That's why I have to do absolute value.